Good afternoon, everyone. Welcome to our hydraulic fracturing stimulation webinar. First, we would like to introduce our company. Megaplus Oil and Gas Solutions Company is a leading provider of geoscience services, oil and gas training, and consultancy solutions designed to empower energy professionals and companies worldwide. We specialize in geophysical, geological, and petrophysical services, such as seismic interpretation, reservoir characterization, seismic inversion, and advanced subsurface analysis, reservoir engineering solutions, which is dynamic modeling, reservoir simulation, and enhanced recovery strategies. Oil and gas training and certification, we provide expert-led courses in petroleum geoscience, reservoir engineering, and data science applications in the energy industry. Our mission is to deliver cutting-edge insights, innovative solutions, and world-class training programs to help professionals enhance efficiency, optimize exploration and production, and drive success across the energy sector. Join us to stay updated on industry trends, upcoming training program, and exclusive insights. Contact us for any consultancy services, corporate training, or collaboration opportunities. We are very pleased to welcome Engineer Sikfi Hamilton Aspinant as one of our distinguished instructors. Engineer Sikfi is a versatile petroleum engineer and educator with extensive experience in reservoir management, drilling operations, and offshore QHSE across complex international environments. He has a proven track record in delivering technical training and risk management frameworks, combining engineering expertise with data technology and automation. He focuses on data-driven decision-making, workflow optimization, and operational excellence. His multidisciplinary background enables him to bridge engineering practice with modern digital analytical solutions. If you have any questions across the session, please write them in the chat box, and Engineer Sikfi will discuss them when possible. Engineer Sikfi, you may share your screen and we can start. Thank you.
Okay. Okay, can everyone hear me?
Yes, it's clear.
Yeah, okay. So I would like you to have a minute or two or three to tell me who you are, what you are working with, or what your work, what if you're a production engineer or if you're a geologist or a reservoir engineer or what you are doing, you can just tell me this. And if you can tell me what company are you working for and the field if you want me to put the real data into the presentation on the next session.
Okay, my name is Ali Shendi. I'm a petroleum engineer, but now specialized in drilling flows and cementing. I am working as drilling flows and cementing advisor for Petrogas Rima in Muscat, Oman.
Okay. And the next, Martis.
Hello.
Hello.
I'm a student in petroleum geology in France.
Okay. Ali. Okay, next you can go, Ali, if you want.
Hello, everyone.
Just tell me what you're working. Are you a geologist, petroleum engineer? Or if you can jump to next person.
Hello everyone, I am
Hello.
Malaika Begum and I am a geophysics student. I am doing my master's from Qaid Azam University, Islamabad, Pakistan.
Okay, cool, interesting.
Hello
Next.
everyone,
Mhm.
this is Hiba, reservoir engineer. I work within Sonatrach, Algeria.
Okay, many different companies. Yeah, that's cool.
Hello, everyone.
Hello.
Hello.
Hello,
Good
hello, everyone.
evening. I'm Endra from Jakarta, Indonesia. I'm a drilling and well service specialist Drilling Division, SKK Migas, Authority of Oil and Gas Industry Upstream. Thank you, Mr. Aspelun.
Yes? Yes, what was the question?
Hello,
Okay, is there anyone else who wants to say something? Yeah, come on. There any more? Okay, we can continue with the hydraulic fracturing stimulation. Is there any one of you that is working with hydraulic fracturing at the moment, or will do, or have been doing this? Is there anyone who is familiar what hydraulic fracturing is? How you can explain it? It is with few words, sandstones, chalk is high permeability in it and high porosity. Shale is also higher porosity, but the permeability is very low. So basically, we were pushing the water and the other chemicals into the formation to fracture the shale. It will be opening like a small channel going through, and then you can put in sand to keep it open, so the oil can get through into these channels and up. This is a relative new technique that is not too old. In United States of America, they were producing a lot, and in the 90s, they got this bell-shaped curve. The oil production went downwards, and then they started talking about how they could increase the production of oil. And they were finding someone was smart enough to think about pushing the water into the shale and crack it so we could get a lot more oil. And if you can see this famous bed structure, the oil was coming straight up, and it's not pointing down as far as I know, because there's a lot of shale gas, shale oil in the United States of America. Okay, what is the hydraulic fracturing? It's a high pressure fluid injected into the rock formation. Basically, it's for shale because of the permeability is low, and you don't need a sandstone permeability risk because it is permeability in sandstone or chalk. It's a very, very, very low permeability fields that needs this. And it's creates enlarges fracture because of the pressure is higher than the formation pressure, so you can get the fractures and oil. And it reminded me about some mathematics, some fractals that is going into the shale. It's it's something that if you're interested in mathematics, you can learn by reading about it. And of course, as I said, it's increasing oil and gas flow to wellbore, so it's recoverable, and it's reducing the expenses, or you get more oil, you get higher income, and then you can continue with this fracking. And it's essential for tight and shale reservoirs, as I said. And process of fracturing. That's first we are drilling a normal well, and you are putting making the cement job, and then you are perforating, and then you are doing the fracking job. And this is after the well drilled and the perforations. And this fracturing fluid, which is much a lot more, a lot of the times is water. They also have other fluids to pressure fracture the wells. And the propan is injected to keep these fractures open. You can also use sand because sand is high permeability. And the pressure is raised. Fractures remain conductive, and then you get oil and gas production. There's some places in the world that is a lot of shale oil, shale gas. It's not only in United States where there's a lot of this, but it's also in Kazakhstan. I was working for Kaspi University, where there was people from the oil companies coming, and I was teaching them about where it was shale gas and shale oil, and a little bit of fracturing technique, of course. But there's a lot of shale oil and shale gas in the world. I have a presentation on the internet that I could show more from that from the next step, which is a course. So I can use this information that I already have, redo it, and with also, of course, new information. And if I can use your information in the next presentation. And rock mechanics and fracture creation. This built-in situ stresses control fracture orientation. As you can see here, this is a horizontal well, and then we have these holes from perforations, and you squeeze this fluid into the formation. So it's vertical fractures, and you can see it's not only one straight fracture out there, but it's like the fracture is going to the left and to the right in front from the main fracture, and this will increase the permeability a lot, and then you get a lot of oil production from that, and gas, of course. And the breakdown pressure indicates fractures. If the pressure is stopping, and then you have these fractures into the well or into the reservoir. Propagation and closure pressures, and you have vertical fractures in deep formation. That means that you can make a long fracture. And in United States of America, I can see on the YouTube videos that they are having problems to their drinking water because the oil field and the fracking is very close to where some people live. And then you have had gas coming into the water system, and they could use a lighter to ignite this so it is burning. And this is not a very healthy situation. Either they have to move to another place, or they should do something about the water, like they're buying a big water tank, like you have in Indonesia. They're using big water tanks, and then they're drinking from that. well construction and perforation design. Here you can see perforated holes from the so it's making holes into the well, but you are squeezing the water in from the well and into the formation through these holes and making these fractures. And you have this. This is of course steel that you have like a TNT dynamite. So you're exploding through this steel, and you have a cemented well design, and you have a multi-stage completions for horizontal wells. Horizontal wells are very popular today. In the past, they were using vertical wells, and there was a limit how much oil they could produce, so they could use this technique here. But today they are more or less drilling horizontal wells. I was working as a mudlugger geologist offshore with geoservices for a Statoil rig or reservoir. Now today they are Equinor, and we were drilling a very long section of horizontal deviated wells, and I think it's one of the longest horizontal well in the world, or at the moment when we were drilling it, it was maybe it was the longest one, but there's coming many others after that is longer. And you have the cluster spacing and shot density, so you have to calculate the size of the hole and the length between them, so that you can optimize your oil production. And you can also have techniques of placing different wells in different areas to optimize the oil production. So it's not getting oil production from they're not stealing the oil from the other. So like they are far enough to not interfere with another well. So I remember I was reading this in reservoir engineering, but I don't remember any equations or anything like that. But I remember I was reading it. And you have a zonal in isolation techniques. That means that you are having zones where you don't produce, they are isolated. Okay, you have fracturing fluids. You have a well here, and you have an aquifer sandstone, aquifer in a sandstone, and you have a water aquifer here. Here is shale, I would guess. So we don't want to produce this aquifer, the water zone. So they are producing from the sandstone first, and when the sandstone oil is declining, and then perforating another time, and they get oil from that and fracturing it. And maybe when they're finding this area, they are making a lot of horizontal wells for production optimizing. And you have water systems, water-based systems, which is 90% of the fracture-based fluid. And you have friction reducers, and you have gelling agents and breakers, and you have biocides and corrosion inhibitors. We were using this in Talisman when I was working there as a production engineer, and there was a lot of algae or bio life that we had to put into the field to kill this. This was on a wild field, and we also used the corrosion inhibitors, so there will be no corrosion between the chemicals coming from the injector, water injector, towards the chemicals that is in the reservoir, because we are using fresh water to inject. So we did that once a month, I guess, doing these jobs. And you need profane selection and transport. You have a natural sand, ceramic, or resin coated. And then you have maintains fracture conductivity. Conductivity means flow transport in a high permeability area. Then you have a high conductivity. If the conductivity is low, that means the permeability and the porosity is lower. And you have a size and concentration critical. So if you have higher or lower concentrations of the fluids, and then you have keep fractures open long term. If you are just pushing in the chemicals and the water into the shale, it will if you stop fracking, it will like fall because of the pressure. It will be closed. So you have to use something to keep it open, and the sandstone is one of them. So these fractures are not getting back to the clay. So you have to start. This probably happened when they started doing this. They didn't know that the fracture would collapse, and then they do it, and then they have to redo it. I don't know this history, but I can imagine it's something like that. And yeah, and the treatment, design and diagnostic is important that you need to have the same treatment of chemicals to do this job right. If you do it wrong, maybe you have to do it another job, and this is costly jobs. It's nothing that you are doing in 1, 2, 3. It takes a lot of time and making plans of it, and get people on board and everything that they need, the chemicals and everything. So this is something that you have to do right the first time. There's no reason to make experiments. You have this pressure, temperature analysis. Of course, if you have been producing oil for a long time, the reservoir pressure will drop, and then you have to, of course, you get to have to measure the reservoir pressure continuously. So when there's a high pressure, of course, this fracture will be closed earlier than if it's not that high pressure. So that's the reservoir engineers and production engineers. They like to know how high the reservoir pressure is. And you have this microseismic monitoring. I guess that everyone knows what the seismic is, that they are sending this different sound signals. You have this MWD tools from Baker, Halliburton, and SLB now. They are running this. I've been working with these people with MLD tools, and they are doing many different signals. But here is seismics, which is sound into this reservoir, and they are recording the seismics, the sound that's coming back, and the harder the rock is, the faster the sound speed is traveling. And then you can analyze if you have what type of minerals do you have in the well. So if you have sandstone, claystone, chalk, and tuff and everything, you can get the data from this, and someone who knows what they're doing in this field, that they are analyzing the what kind of stone rock you have. And this is important because if you want to do a fracking, you have to find the shale, and then you have to fracture the right place and do everything right. You don't have to make fracturing in sandstone or claystone, because it's okay data with permeability. And we can also make a 3D model of this, so you will understand. Like my first job was as a geoscientist in Oppsal. I was working with RMS modeling tool, where you put in seismics and rock and everything that you need for your design. So you can put, for example, well design, fracture design, or lithology, what kind of lithology you got. And yeah, it's a quite interesting tool that is owned by an American company today. And Petrel, which was made also in the same street in Sandnes, Norway. Then they were sold to Schlumberger or SLB now. And Amazon, there was a company who's buying RMS for Oxar. And fracture length, height modeling, you are making a design, how much you have to know what pressure it is in the reservoir pressure. So know how much pressure you need on the squeeze, and then you're designing how long the fractures are going, so they are not too short. That's the most important. It's not too short, but they cannot make fracture forever. So they cannot be that very long. So they have to optimize it and compare to what you get back from it, how much oil you get back from it. And then you have a production logging evaluation. And when you're doing this job, you're analyzing how much more oil you get. For example, when I was working for Talisman as a production engineer, I was using this Enbal, Prosper, and Gap. The Enbal was not that important, but the other tools I used every day to analyze the pressures and how much what we can do to get more oil from the reservoir using gas lift valve, for example. And with this method, we can use to analyze how much more oil we got from this fracturization. Okay, you have environmental and regulatory aspects, as I said before, when the people who is living next door, close by, they got the gas from the wells, and from the drinking water, they could get some small parts of oil. So this is a very unhealthy thing. They get cancer from that if it's not noticed, if you don't check it. So this not a good thing. I was working as a QHSE engineer for Ocean Rig, the drilling company, now bought by Transocean. And I was focusing on different aspects of what can destroying people's health. For example, falling objects and chemicals. I was also working with injected emulsified polymers, bullheaded into the reservoir to put in a gel or emulsified gel into the reservoir. It's quite similar to fracking. And then we use this gel to gel up with the water part so that the water part was staying in. So you reduce the relative water permeability and you increase the oil production and relative permeability of oil. It's not the same, but it's bullheading, and bullheading is often used in fracking. And the water sourcing and management, you have to know how much you need of this porphyry, how much water you need to fracture the wells. Everything has to be planned. So everything is going to so every plan is going correct way, and you don't have too much, because if you have too much fluids on the rig, you have less space from another thing and materials that need, for example, chemicals or bits and everything that you need for drilling a well. So keeping this if you keep this one correct all the time, then you can ask for the boats, shipping boats coming in, new in out with this, and then with the oil tankers, you're making a plan for that. I was doing that in Talisman, making a plan when the oil transport ship can come and pick up the oil. So it's important that every aspect in petroleum engineering is going well. I guess that someone of you are working onshore. I'm working offshore in Norway and in Greenland and Ghana and in Iraq now recently in one of the biggest fields in the world. Yeah. That's all offshore field because Iraq doesn't have all offshore fields. Majnoon field. You have this chemical handling and disclosure. The profound, you need to know how much you need for your fractures and transport from ships. There's not only one thing that is coming with transport ship, there's many things. So you have to optimize, you have to plan, everything has to be in place. Flowback and produced water management. That's just a part of what I said now, is maintaining the correct volumes. You have well integrity, that means that if the well integrity is high, that means it's probably new and the production is going well with the high permeability. If you're using chemicals to the formation, that you can reduce the well integrity. For example, cement. If you're putting cement into too much cement, then you will reduce the well integrity. And induced seismic monitoring. If it's disturbed, then you will get a bad measuring moment there. And you have regulatory compliance and reporting requirements. In case there is some issue with health, safety, and environment, then everything has to be sent to the government. This is in Norway. I don't know all the regulations in all over the world, but if case I was working offshore as a QGC engineer for Ocean Rig, there was hundreds of mistakes, errors, and small and bigger HSE issues, steel coming down from the derrick and could kill a person. Why do this coming? Because they are drilling on something hard, and then you get bucklings from the well pipe, and then I was talking with the Roxa. No, Geo Services. They said that there was a steel spoon coming onto the shakers. And when I was walking to the doghouse, I saw there was high spikes on the drill floor. And that means that there's something wrong. And there still is something wrong. And later I heard that they have milled on the BOP, and that's an extremely dangerous situation. So this is very dangerous, and of course you need to drill a hole first when you want to have a horizontal or deviated well, and when you want to do the perforations, you don't want to have a destroyed BOP. This was in Greenland. So everything. I was also working for GeoService on Ocean Westvanger, and we got a kick, so we had to cut the anchors and drift sideways, and we were just above the gas zone, so the gas were coming up, and we had a double hurricane, so we had to be evacuated before we tip over or something. So we don't, if you're not doing it the right way, they are displaced from the oil mud to water-based mud. So when the kick came, we have to drift away and get away. And of course, when you want to fractures, you want to drill a well as well as possible, because you don't want to kick when you're doing a fracturing job, because it can easily be a blowout. The same rig has been in a blowout on another name called West Vanguard. And you have this well integrity and induced seismic in monitoring, of course, the regulatory compliance and reporting requirements. Everything, all the HSC incidents or small incidents or possible incidents has to be reported to the government. And you have key design parameters. You have critical pressures like breakdown pressure. You have the propagation pressure, and you have the closure pressure. This is things that I would like to dive into in the next session in a 5 or 7 days courses. And you have this fracture geometry, which how long it is, I've already been talking about, and the height, how long it's going from the fracture itself and going up and down, and the fracture width, how wide it is, and the conductivity. Conductivity, that means when you have a high permeability field, it's high conductivity, and when you have a fracture reservoir, you're having increased the conductivity, and that's what it's all about. It's the increase in permeability that makes a better conductivity. That's a fracture geometry. You have unconventional resources where you have shale gas, shale oil, and tight shale stone. You have the marcellus Barnett and Eagle Ford Formation in United States of America. They are huge. And you have tight oil in Bakken, which is a Permian basin. And you have a coal bed methane, means that you have coal in the reservoir. You can make a perforation, and then you can produce from that also. And CBM development. You have permeability to low without stimulation. Natural permeability to low that you need to increase the permeability. Multi-stage fracturing, maximizing reservoir contact. And as I would like to do for you, making a real world case studies. So if you are sending me a list of the oil companies that you're working for, I could make a real case that you can make, take a real issue from that you have from your company or something that you could have. So we make a group and asking each other questions, making questions, and we're trying to make a plan, a real situation from drilling to fracking or anything. That is real. I can find information online, which is easy. Sometimes we can find a lot of information. Sometimes they want to keep a secret, and they don't want to put it on in internet. But in Norway, there's a lot of information that is online. And when I was going to make a presentation of in North Iraq, then there was a lot of information that I found. So something of this I was reviewing. Iraq was because the first time I didn't go because of ISIS was around the city then. And you have a shale gas success, like the unconventional resource breakthrough with multi-stage completions. That means setting a whipstock and drilling into another formation and making more money from one well. And then you have a tight oil development, which is economical production from low permeability formations, which I've been saying many times now. Okay. Key takeaways. Hydraulic fracturing enables economic production from tight formations. That I'm saying all the time. That's oil, coming more oil from hydraulic fracturing, and then you sell oil, and then you're getting a better economy. And sometimes I see in the news that OPEC is increasing oil production. Then the production is going down, or the oil production is going up, and the oil price is going down. So where is the perfect spot where you can maximize this? If you are producing low, the oil price will go high, but you are getting too low volumes. So I've been thinking about that. It would be cool if anyone who were making a study on that. That could something that I could do in in an oil company. That would be very interesting because I like the mathematics, physics, and economics behind it. You have the hydraulic fracturing enables economic production from tight formations. Multidisciplinary approach. You have geology, sandstone, claystone, limestone, tuff, anything. You have the engineering. You have to plan the drilling the wells, and you have to planning the job for for everything. When you are making the wells first time, you have to put the right equipment inside. For example, gas lift ventils, gas lift valves, and you have to design the well first, and you design the fracking job. And in long term, you need to know how to deal with high water cut. I was working with at Vaget with very high water cut, and that's opportunity to make a fracture job in another zone that they started to produce the first times. And environmental, then I have already been talking about that. It is coming chemicals in the drinking water. There's something leaking and gas into the outside the water. And you have a careful design. You have to optimize how much dynamite you have to use to get the long length of the fracture that you want to optimize the production. And ensure success. You have this stewardship essential for sustainability. Sustainability is mean that is working a long time in an easy way to say. Okay, thank you. I was a little bit faster than I expected, or you expected, but I'm happy with this. And do you have any comments? Hello?
How can the turbine, how many pump we need to do the job, doctor?
How you can plan it? You can, for example, use a simulator, and then you can making different sizes from your fracture. And this is somebody who has been studying physics, a lot of physics, can make a software. I'm studying data technology, making programming, so it's not an easy task to do because you don't know how many fractures you can get. You need to know something about the rock mechanics and everything, what hardness it is. A mod logger would find out if it's hard or soft, and you have to simulate the physics behind the fractures that you want. But this is a very, very complicated thing to do. Okay, anyone else having comments? I think that they're not listening or finished.
I have a question.
Yeah. Do you have a
Yes.
comment?
Yes, in comment, my question is what is the criteria to decide either to go with proppant frac or acid frac?
Of course, that has everything to do about the lithology you got. Like if you want to do acid job, I was out offshore in Norway on a chalk field. I think it was BP Ula or Valhall or something. It probably Valhall, and I was there. I was seeing some coiled pipes, which was going into the well, and I was asking some person that was working there. He just passed by me, and he explained what they were doing. They were doing an acid job. They were using HCl, which is a very toxic acid, and they are putting this by cold tubing into the formation to dissolve this chalk. Maybe it's sandstone with a lot of chalk in it. So they would wanted to dissolve this to produce more oil. This is for this salt acid jobs. It's quite similar to a fracturing job. It's just a matter of how much pressure you're putting it. If the pressure is high and making fractures, then it's a fracture job. If the pressure is lower, then it's going into the formation pressure, and then you don't have a fracture job. You just have a acid job. The profond is normal. It says 90%. If you do not have chalk or limestone, you're wasting your time with acid, because acid is dissolving chalk and limestone. There's also a quite similar mineral to the dolomite, which is dolostone, which has a kalium atom in the system there, and then it does not fizz with using acid, but they look quite the same, limestone or dolostone. It's difficult to see the difference from them. But when you are using, I was metallurgist, geologist, putting acid onto the formation, it was easy to say, oh, this one is fizzing, this contains limestone, chalk. This one does not. This one is non-acid dissolver. Dolostone will not fizz.
It's usually used with carbonates, the acid fracturing, right?
Carbonate, that's limestone and the one that I was just talking about.
And excuse me,
limestone chalk, that's carbonate.
how can we ensure that the acid that we're pumping, or the frac acid, is going in the
formation?
Into the formation, but in a very fine direction. It's not dispersed.
It's when I was working with this emulsified polymer job, I was told to follow the pressure, because when you're putting the pressure down the lane, it's not increasing or decreasing. And then when you're putting this formation into these chemicals into the formation above the pressure will increase into you get the fracture pressure. And when you got the fracture pressure, you will stay on that pressure, and then you get the fractures. So what's the answer to your question is that you can see a spike on the pressure. It will increase because you push something that doesn't want to be pushed, and then they are going into the pores, and then it's resisting, and then the high pressure would come, and then it's flowing into the reservoir, and then that's how to find out. And of course you record pressures, temperatures, everything.
Is that for carbonate or sandstone?
From
is that what you're talking about? Is it about
this is any, if you're going into chalk or sandstone, it will the pressure will increase, of course, because as you go into in the formation, it doesn't stop and ask what kind of formation is. It's just that the pressure is higher in a small permeability. It's like chalk, limestone. It's got if the permeability is lower, the pressure will be higher. And then you can see, oh, this is rock. What kind of rock? This is sandstone. This is limestone. This is claystone. Because you record all this data, the
But how
pressure data.
but how we can ensure that we are creating the wormhole into the formation, and we are not spending the acid elsewhere? I mean, is it
Oh,
any chemical that it's mixed with the acid, so we can ensure that we are creating the wormhole instead of just pumping acid and it's going everywhere and it's
okay. I think
reacting with anything in the formation. You
I think
understand my?
hmm?
Did you understand my question?
I think I do. I think I understand. When you are, I was thinking about another job that can be an analog. When you're drilling an oil, you want to drill it with mud, drilling mud, water or oil-based mud, and then you go into the place that you want to go to, and then you put the casing, make the well, and then you want to cement the job, and then when you are going from sandstone, from drilling mud to cement, you have a spacer in between it. That means it's a cork or a screw or something that doesn't make these chemicals react with each other, because this is important. Because you don't want these two to be mixed, because it will be destroying the way how cement is settling. So when you are pushing the cement, you have on the behind, you have another spacer that is, for example, water that is producing or drilling fluid. So that you can put the cork in, and then you can get the cement out into around the wall and into a little part of the formation. And I think that's exactly what they are doing with the acid job, that they are putting the same screws, because you don't want to mix formation water or regular water and acid. You have to have this spacer, so you can keep the fluids away from each other. And acid, why do we use acid? Okay, we need acid because there's a limestone and chalk. These are dissolving. It's like you get, when you put a little bit of it in a tray for geologists, you can put a part of it, a small drop of HCl, hydrochloric acid, and if it's fizzing, bubbling like Coca-Cola, it means that it's an acid has worked on it, means that it's dissolvable from acid. For example, limestone and chalk. The first oil field we found in Norway was in 1969, which is from Ekofisk. There's not too many of these in Norway. I've been on Valhall, working there. The most difficult reservoir to drill in, and I think it's high limestone chalk. And then when we are drilling there, they just had to set a new fracture, because this was falling down into the wall. And you can think that this is a big fracture, like a big hole, and then you are squeezing something into it to make small fractures. And when this acid is meeting the limestone, and and claystone, you dissolve it. It's becoming very soft. It's not a hard rock anymore, so you can drill easily or not. Because the Valhall you were using is whipstock, like 5, 6, 7 whipstocks in one well. So I didn't do any jobs in 2 weeks then. Another time I was in the same place, we were drilling very fast, so we had something to do all the time. So it depends of what kind of lithology you have and how the well is responding to your bit and your pipes in the well, and then that's the main issue. You have some lithology that is reacting to acid, and those are not active to acid. And it's important to make a log as a geologist, writing down what it is, what the color is, what the angle is, what sphericity, what the if it's a sphere, if you can see through it, exactly everything about the information. And then there's two different lithologies. You have limestone and dolostone. These are almost the same thing. It's just that in dolostone is kalium or potassium. We will say kalium, but in English it's potassium. This one is not reacted to acid because of potassium, potassium magnesium oxide or something like that. And then that's why we find out if this acid will react or not onto the formation. So if you have dolostone, there's no reason to do a acid job. But if you have this limestone, which is dissolved by acid, then you can have a acid job to make a better permeability, of course,
Thank you so much.
factoring. So was that the answer to your question?
Yes, thank you so much.
Thank you. Anyone else who have a question? No more question?
All right, everyone. This brings us to the end of our session here with Dr. Sikfi. Thank you so much, Dr. Sikfi. Thank you, everyone, for attending and for your participation. And we hope to see you in our upcoming webinars. Thank you, everyone. Goodbye.
Thank you.
Thank you.